So, good morning, all. Let's continue the yesterday's problems, whatever we have studied. So, let me put in slideshow. So, last we have studied about the CPM, okay, mean molar heat capacity. In that, if there is CPM, mix 1 and mix 2, okay. So, like this, we have studied about for this in here. If you are having two in CPM only, if you are having a mixture of gases, how we have to do, we have studied. So, we are going to continue the problems related to that only, okay. So the next problem is a stream containing 10 percentage CH4, a stream containing 10 percentage CH4 and 90 percentage air by volume. Okay, so consider here it is by volume is given. So we can consider mole percentage is equal to volume percentage, no problem in that. So we can consider that. Okay, mole percentage is equal to volume percentage, we can consider that. So take T1 is 373 Kelvin, from 373 Kelvin to 573. So T1 is 373 and T2 is 573 at a rate of 0.05 meter cube NTP per second. That is N is given as 0.05 meter cube NTP per second. Okay. So now we have to calculate the heat required. Okay. That is Q we have to calculate. They have given the Cp naught M value and Cp naught. So this is Cp naught M1 and this is Cp naught M2. And from this we have to find Cp naught mix Cp naught M of mix 1 and here we have to find Cp naught M of mix 2. Okay, usually higher temperatures will be mix 2 and lower temperatures will be mix 1. Okay, and one more thing is N is given as meter cube, okay, per second, okay, meter cube per second. So N is given as 0.05 meter cube per second. Okay, so I have told you how to convert. Divide this by 22.4 will give you in kilomole per second. So now n will be 0.05 divided by 22.4 will give you the answer is 2.232 into 10 power minus 3 kilomole per second. Okay, into 10 power minus 3 kilomole per second. So now first we have to find the Cp naught, C naught Pm of mix 1. Okay, so that is sigma xi Cpi naught mi. Okay, so x first we have to find x all this. So x ch4 is 10 percentage, so 10 by 100. So you will get as 0.1 and then next is x air. Okay, this what 90 percentage, so you will be getting as 90 by 100, so you will get as 0.9. So now Cp naught M of mix 1 will be 0.10, okay, into 37.5974 plus 0.9 into 29.2908. So now zero point 0.1 into point, just, just a second, zero point 0.1 into 37.5794 plus 0.9 into 29.2908. Okay, so the answers will be, you will be getting answer as 30.1215 kilojoules per kilomole Kelvin. Okay, and the next is C naught PM of mix 2. You have to find C naught PM of mix 2, same way sigma xi CPI. So here you will be getting as zero point 0.1 into 43.0821 plus zero point 0.9 into 29.6132. Okay, so you will be getting it as 0.10 into 43.0821 plus zero point 0.9 into 29.6132. So you will be getting the answer as 39, sorry, not 39, 30.9601 kilojoules per kilomole Kelvin. Now you have to write the formula for Q. Q is equal to N Cp naught M of mix 2 into T2 minus T0 minus Cp naught m of mix 1 into T1 minus T0. So here we know the temperatures. So this is T1, this is T2, and this is T0. 298 Kelvin is T0. Okay, so now substitute all the values and find the answer. You will be getting the value as Q is equal to 13.961 kilojoules per second you will get. Okay, so because the N is in kilojoules per kilomole per second already, so you will get the answer in kilojoules per second. So the answer, final answer will be 13.961 kilowatt. 13.961 kilowatt. Okay, and same method, the next problem. Okay, so the gas having the following composition by volume is at temperature. Okay, so here T1 is 773 Kelvin, and they have given the compositions as SO2 is equal to 7.09 percentage, O2 is equal to 10.55 percentage, SO3 is equal to 0.45 percentage, and N2 is equal to 81.91 percentage. Now we have to find the heat content of 1 kilomole gas mixture, that is N is equal to 1 kilomole gas mixture over 298 Kelvin using the mean molar heat capacity data. So here, like how we have done Cp naught m only previous first set of problems. Okay, so just remember, so here when you do this, here Cp naught m, you have got two values, that is Cp naught m2 and m1. And the next problem, we have got only one Cp naught m value. Same way here, previous two problems, we have Cp naught mix, two mix. But here you are having only one mix. In this problem, you are having only one mix. So the formula will become as Q is equal to N into Cp naught m of mix into T minus T0, if there is only one mix. So, but we have to find the Cp naught m mix. Cp naught m of mix is what? Sigma xi Cpi naught. Okay, sigma xi Cp m. Sigma xi Cp naught I of m. Okay, so now for this you have to find Cp naught m of mix. Okay, and then you have to find the substitute in the formula, and then you have to find. So here T will be 773 and T naught will be 298 Kelvin, and N has been given. And first you have to find X SO2, XO2, all this. So X SO2 is, so X SO2 is 7.09 percentage divided by 100. So you will get as point 7, sorry, 0.079. Okay. Okay, and the next is XSO2, and the next is find XO2 and find XSO3. Okay, then find Cp naught m mix. Okay, when you are substituting Xi Cpi naught m, so you will get the Cp naught m of mix value as 31.4548 kilojoules per kilomole Kelvin. Okay, and the next is Q is equal to N into Cp naught mix of this. You people do it. Okay, same step into T minus T naught N is 1. So this Cp naught M mix value you substitute here, that is 31.4548 into 773 minus 298. So you will be getting the answer as 14941 kilojoules. Okay, nothing difference, only thing is instead of two mixed values you have got only one mixed values. Okay, that is the difference. Okay, and the next problem is, so chlorinated diphenyl is heated from 313 Kelvin to 533 Kelvin. Okay, 533 Kelvin in an indirectly. So T1 is this, T2 is this. Okay, in an indirectly fixed heater at the rate of 4000 kgs per hour. Here instead of number of moles, it is given in mass. Okay, calculate the heat required to be added to the fluid in the heating coil. the heat capacity of the fluid in the temperature range is given below. So Cp data is given as C, nothing else. They have given the Cp data. Okay. Only thing is the same formula, that is Q is equal to N T1 T2 Cp dt. Okay, instead of that, here it will be Q is equal to M into T1 T2 C dt. Okay, Q is equal to M into T1 T2 C dt. Same, the previous problem, the first set of problems, whatever we have done, the same method is this. Okay, so now instead of formula is Q is equal to M into T1 T2, instead of Cp you are having C, that's it. Okay, so write the formula M into T1 T2. C data is given 0.7511 plus 1.465 into 10 power minus 3 t, okay, into 10 power minus 3 t dt. So now this can be written as M into 0.7511 into T2 minus T1 80, okay, plus 1.465 into 10 power minus 3 by 2 into T2 square minus T1 square. Now M is given as 4000 kg per hour, T1 is 313 Kelvin, T2 is 533 Kelvin. Substitute the values in the above equation. You will get the answer as 369. M is in kg per hour. So we have to convert it into kilojoules per. You will get the answer also in kilojoules per hour. Finally, you have to convert it into kilojoules per watt. Okay. So final answer you will get it as Q is equal to 335.08 kilowatt. This convert after conversion everything. So remember, M is kg per kg per hour. So you will get the answer is in kg. Whatever answer you are getting, you will get in kilojoules per hour. Convert this into kilojoules per second. Okay, that one thing you have to do it. So Q is equal to 335.08 kilowatt. Okay, so this will be the final answer. So all these are related to the heat capacities. Okay, so three different sets of formulas. Q is equal to N T1 T2 Cp dt. Okay, another one is Q is equal to N T1 T2 Cp naught. Okay, Q is equal to, the next set of problems are Q is equal to N T1 T2 Cp naught mix dt, and the next is Q is equal to N T1 T2 Cp naught M2 into T2 minus T0 minus Cp naught M1 into T1 minus T0. So this is for individual gases. Suppose if there is a mixture of gases is there, this will become Cp naught M of mix 2, right? This will become Cp naught M of mix 1. So this formula is sigma xi Cpi naught, Cp naught M. Okay, same way this. And here it is sigma xi Cpi naught. Here it is Cpi M, here it is Cpi naught. And always Cp naught value in the form of A plus Bt plus Cp square plus Dt cube. This you people remember always. Okay. So, and the next concept, so this is all about the heat capacity of gases. And the next concept, what we are going to do is standard heat of combustion definition. What next definition, what we are going to study is standard heat of combustion. Okay, standard heat of combustion, that is del hc. Okay, standard heat of combustion, del hc. So what is the standard heat of combustion is? The standard heat of combustion of a substance is defined as the heat of the reaction of the substance. Okay, it is defined as the heat of the reaction of the substance, defined as the heat of the reaction of the substance, okay, with molecular oxygen to yield specified products with both reactants or products or in the standard state. Okay, when there is the both the molecules, whether both the products and reactants are at the standard state, okay, then whatever the yield we are getting, we will be calling it as the standard heat of combustion. Okay, so the next concept what we are going, that is being represented as del HC, and the next concept is Hess law of constant heat summation. His law of constant heat summation. Okay, his law of constant heat summation. His law of constant heat summation. Okay, so usually it what does it this law states, that is the enthalpy change. Enthalpy, you people know, it will be represented by del H. The enthalpy change, okay, in a particular reaction, okay, whether it is absorbed or whether it is heat is absorbed or evolved, the enthalpy change in a particular reaction is same. Okay, whether the reaction take place in one step or single step. Okay, a gives B also, this enthalpy change is going to be the same. A gives A1, A1 gives A2, and from there B also the reaction is going to be the same. The enthalpy change is going to be the same. So what does this law states is the enthalpy change, okay, in a particular reaction will be the same whether the reaction takes place in a single step or the reaction takes place in a multiple steps. Okay, and as per this law, the heat of the reactions can be added or subtracted, okay, to get the final equation. That means if you are getting A del H1, del H2, del H3, so del H can be written as del H1 plus del H2 plus del H3. Okay, this is what this Hess law of constant heat summation explains. Okay, so now we are going to derive an derivation. So according to this, A gives B, okay, and then A gives C, C gives D, and then D gives E. And from here you will get it del H, del H1, del, this is del H1, del H2, del H3, del H4. Actually, the A gives B. This is single step. Okay. The same B can be produced in a multiple step as A gives C. From C, it gives D. From D, it gives E, and E gives B. Okay. So, whether it is single step or multiple step, the enthalpy change is going to be the same. That is, del H will be equal to del H1 plus del H2 plus del H3 plus del H4. Same way, whether it is in single step or multiple steps, the enthalpy change will be the same. Okay, so the path 1 will be what? This is path 1, A directly giving B. And the path 2 is A giving C, C giving D, and D giving E, and E gives B. Okay, this is the path 2. Okay, this is the path 2. So according to the standard Hess law of constant heat summation, the change in enthalpy will be constant whether it is saying in taking place in single steps or multiple test steps, so that the del H can be written as, so del H1 plus del H2 plus del H3 is equal plus del H4. Okay, so now for example, what we can show is C plus O2. Okay, C plus O2 gives CO2. Okay, this is for this the standard heat of change enthalpy changes del H. Okay, same reaction. Okay, this is one path, one step reaction. Same reaction, it is taking place in two steps. C plus half O2 gives CO. Okay, for this the enthalpy change is mentioned as del H1, and next step is 2CO plus half O2 gives CO2. Okay, the enthalpy change here is del H2. So now this is equation 1 and this is equation 2. Okay, so now we are adding equation 1 plus 2. You will get it as C plus O2 gives CO2. Okay, so that del H will be equal to del H1 plus del H2. Same way, this principle. Okay, the change in enthalpy. If it is suppose 1 minus 2 means if you are getting C plus O2, CO2 by means of 1 minus 2, then del H will be equal to del H1 minus del H2. It depends upon the method, what is the answer you are going to get. Okay. And the next is standard heat of formation. Standard heat of reaction from heats of formation. Okay, standard heat of reaction from heats of formation. Okay, so the standard heat of reaction, okay, the standard heat of reaction, that is del H0 R, is being defined as the summation of standard heat of formation of products minus standard heat of formation of reactants. Okay, so this is called as the standard heat of reaction. Okay, standard heat of reaction. Okay, so the standard heat of reaction is defined as the, okay, difference between the algebraic sum of the standard heat of formation of products minus standard algebraic sum of the standard heat of formation of reactants. Okay, this formula you should remember very well. The standard heat of reaction formula is standard heat of formation of products minus standard heat of formation of reactants. Okay. So related to this, okay, related to this enthalpy and standard heat of reactions, we are going to see the problems related to this. Okay. So the first problem under this is we have to calculate the heat of formation. Okay. So we have to calculate the heat of formation of N-propanol liquid using the following data. Okay, so they have given standard heat of formation. Okay, del H1. Okay, so the standard heat of formation of CO2 is given as minus 393.51, and the standard heat of formation of H2O is given as minus 285.83, and the standard heat of combustion of N-propanol is given as minus 2028. That means the first two reactions, CO2 in the first reaction, this is a reaction. For a reaction, they have given the standard heat of formation of CO2. That means CO2 is the product. Okay, and the next is the standard heat of formation of H2O. Again, this is also H2O is also a product. And the third is standard heat of combustion of N-propanol. That means propanol is in the reactant. Now for all these three, we have to write the equation. Okay, standard heat of formation of CO2. So we usually know the reaction C plus O2 gives CO2. For this, del H1 has been given as minus 393.51 kilojoules per mole. Okay, for the first we have written, and the next is standard heat of formation of H2O, that is H2 plus half O2 gives H2O. For this, del H2 is given as minus 285.83 kilojoules per mole. Now the next is standard heat of combustion of N-propanol. Okay, propanol combustion means propanol is getting reacted with oxygen. So propanol formula is C3H7OH plus O2 gives plus O2 gives, okay, the combustion products is what? CO2 and H2O. Always you remember CO2 and H2O. So balance it. So you will get as 4.5. Okay. C3H7OH plus 4.5 O2 gives 3CO2 plus 4H2O. For this, the del HC value is given as minus 2028.19 kilojoules per mole. So for these three reactions, okay, we have written the for these three given data, we have written the reactions. Okay, we have written the reactions. Now the thing is, they have asked us to calculate the heat of formation of N-propanol. So in these three reactions, if you see C3H7OH is in the reaction part. Okay, but we want a equation where this will be come in the product side. The C3H7OH should come in the product side. So we should solve these three equations in such a way that C3H7OH will come in the product side. Okay. Always remember, for the combustion, the product will be CO2 and H2O. So what we need is, suppose if you want this C3H7OH in the product side, first we should add these two equations, and then we have to minus from this. So the CO2 and H2O will get cancelled, and we will get the equation with respect to C3H7OH. Okay. So now see, so here you are having 3 CO2. Here only one CO2 is there. Here we are having 4 H2O. Here only one H2O is there. First what we will do is, this is 3 into equation 1 to get 3CO2. Okay, 3 into equation 1. So you will get 3C plus 3O2 gives what? 3CO2. And the next is you want 4H2O. So 4 into equation 2. Okay, so you name it, this is equation 1, this is equation 2, and this is equation 3. Remember, we are going to modify, solve the equations in such a way that N-propanol should come in the product side. N-propanol should come in the product side, and we should cancel all the maximum possibilities. Okay. Hmm? So now 4 into equation 2 will give you 4H2 plus 2O2 gives 4H2O. Now these two you add. Okay. So you will get 3C plus 4H2 plus 5O2 gives 3CO2 plus 4H2O. So, and one more thing I will explain you is, always whatever is in the products, okay, of the other than the combustion reactions, you should try to cancel it. Okay, then only you will get the final answer. Okay, then only you will get the final answer. Now, this equation you subtract with equation 3. What is the equation 3? C3H7OH minus, okay, plus 4.5O2 gives 3CO2 plus 4H2O. So minus of this equation, right? So all this will become minus, right? Minus, 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 minus. So now this will get cancelled. Okay. So you will get it as 3C plus 4H2. 5O2 minus 4.5O2 is plus half O2. Okay. Minus C3H7OH gives nothing. Okay. So now bring this C3H7 there. 3C plus 4H2 plus half O2 gives C3H7OH. Now we have got the equation where we are having what? C3H7 as a product. This is the equation 4. This is the N-propanol as a product. Okay. So first, once again I repeat, first what we have to do means, for the given data, okay, standard heat of formation means CO2 will be in the product, H2 will be in, and standard heat of combustion is propanol will be in the reactant, and this will react with O2, and the products will be always CO2 and H2O. Combustion products already we know. So now these are all the given data. Okay, for this del H1, del H2, del HC is given, but they have asked the standard heat of formation of N-propanol. So we want the propanol in their product side. So what we have done is, we have modified the equations in such a way that we should get the C3H7OH in the product. So first thing is, when you need the reactant in the product side, this should be negative. Then only you can bring it to the positive. That means wherever the reactant is there, that equation has to be subtracted. That one point you should remember. So if you subtract this only, you will get the negative, so that the required thing will come to the next side. Okay, because this will be in the reactant, it has to come to the product. So this should become negative. Then only the product you will get it as positive. Okay, so the equation where you have to find, that is the final combustion, it has to be subtracted. So that you should remember. And the next thing is, whatever the products of this combustion reaction, you should try to cancel it. Okay, you should try to eliminate it. So here you are having 3CO2, 4H2O. So from these two equations, you should try to get us 3CO2 plus 4H2O. So if you subtract from this, you will get the final answer. Same way we have done. 3 into equation 1 gives 3C plus 3O2 gives 3CO2. Same way, 4 into equation 2 gives 4H2 plus 2. So now we have got it, and then we have subtracted from the equation 3. So now how we have got this reaction 4 is equal to 3 into reaction 1 plus 4 into reaction 2 minus reaction 3. Okay, so that means standard heat of formation of N-propanol C3H7OH is equal to 3 into del H1 plus 4 into del H2 minus del Hc. So you have all the values, we have to substitute over here. So 3 into, they have given the values, del H1 values and all, plus 4 into minus 285.83 minus of standard heat of combustion is also given as minus 2028.19. So whatever the answers you are getting to is 295.66 kilojoules per mole, which is the answer for standard heat of formation of C3H7OH. Clear? So the thing what you should remember is, this always they will give whatever we have to find will be in the reactant. So we have to bring to the product side. So always this equation has to be subtracted, and try to whatever the last combustion reaction, you have to try to cancel the products. Accordingly, the previous equations you should modify so that the product of the combustion reaction will get cancelled and the reactant will come to the product side. Same way what we have done. Clear? So the remaining we will see in the next class.